today is Dale Osborn from Midwest ISO. Dale has been here before. I don't know if you remember how long ago it was. 3 years? Maybe 3, maybe 4 years ago. But today he's here to talk about a very exciting topic. He's going to talk about the idea of high voltage DC applications, and we're very eager to hear your talk. And remember, you heard it first here before it becomes reality. So thanks very much.
Don't have to wait for too long, maybe 20 years, it'll be real. Things move at a snail's pace in utilities. Where you point this thing? I started about a year ago working on a subject. NERC and FERC were getting upset about frequency response. In the past, the way frequency response worked, everybody put a little extra reserve on their generator and carried higher pressure and higher temperatures and boilers. So you had some stored energy in the system. Then if you lost one big generator, you could call from that energy base to bring the frequency back to normal. I suppose some of you didn't know we stored energy in the electrical system in boilers, but we do. And with the markets coming up, people aren't paid for that anymore. And if they're not paid for it, they don't do it because it costs money to have extra pressure and extra temperature. There's heat loss. And then you got valve losses when you open the valve. So the boilers are now being run, a lot of them, on what's called once through. They balance the input to the system to the output of the system. There's no reserve. And therefore, the margins are coming down to what's required instead of what was, and people get all upset about that because they think it's the decline. But they gave them market signals to do that. They did it, and now they're upset about it. So that's politics. We had an opportunity to look at that frequency response problem, and I started looking at a way to exchange power with WEC and ERCOT so that we could pool the frequency response obligations of the three areas together and use the DC system to exchange power when one person needed it. The other two would give them a contribution and vice versa. And until this year, it wasn't possible to do that technically because the DC ties couldn't reverse fast enough for frequency response obligations. The voltage source converter, high voltage DC converters that are available now or very soon will be in the 600 kV class and about 2400 MVA. So they're big enough to handle that type of response. Previously, they were listed at 320 kVA and about 1100, and that is too small for most of our regional applications. The other thing that...
What's the rating on your connections between these guys right now? Pretty low, isn't it?
Very low. That's why you have, I'll talk about later how you have to design a self-contingent network between there because the underlying system wouldn't be able to take the outage of one of these larger lines.
WECC is not even more than 200 megawatts.
They're 152,000.
No, you were talking about the capacity, right?
Yeah.
Yeah. So we had an opportunity, and with my experience, I've had HVDC experience. I worked for ABB for 19 years, and I worked for utilities for about 10 years. I worked for Miso for about 10 years. So if you put it all together, if you have enough experience, you see how this stuff works. If you don't have a clue. So I'm one of the few people that is old enough to understand it, I guess, and it won't be that much longer that I'll be around. So
Yeah, we tell them it takes 10,000 hours to become an expert, so you put in your 10,000 hours.
more than that, I'm sure. But what it does is it lowers the customer prices, provides more capacity resource, and also opens additional markets. So there's a business opportunity there, and it's worth about $50 billion. And $50 billion draws flies. People say, well, I want a piece of that. And what you use for your 50 billion is the biggest one is load diversity, and then wind diversity and frequency response. And you can time multiplex those with the energy market, and you can produce a very high value system. The DC can be designed in phases, and the first one would probably be 2 DC lines from Miso south into ERCOT. That's down in East Texas to Texas. Tie our 500 kV system into ERCOT's 345 kV system. And it could be done. The problem with tying to ERCOT is they don't have a capacity market. There's no way to obtain a value for capacity. So we're working on that. So what we're trying to do is work on ancillary service market that does have values associated with it. And it would be with multiple touch points in all three. And I'll get back to the contingency requirements. There's something I call the rule of three. A guy that was retiring when I was starting taught it to me, and I'm surprised very few people know about it. But if you're going to build one transmission line, the underlying system will constrain that loading on that line to the contingency that could be taken by the underlying system. And therefore, it's generally less expensive to build at an existing voltage than to increase the voltage if you're going to build one line. If you're going to build two lines, you can get 50% of that line or more backed up by the other line, and then you have the underlying system. And that usually breaks out about even. You could do it one way or the other. And most people will do it with the existing voltage because they're more comfortable with it. But if you go to three lines, it is almost always less expensive if you can load those three lines economically to build a higher voltage. And the caveat is you have to be able to load them. And so if you have three lines and you lose one, the loading on that line pre-contingency would be 2/3 of the rating of lines. And if you have an AC system in there, it's n-1 times the rating of line plus the AC capability. So you have to build a system that won't overload anything that's there already, or if there's nothing there already, it holds its own contingency. But generally speaking, if you don't have three lines, economically it won't work. And the other thing is to spread them out so that you don't get everything in one area. And when you get to 2,400 megawatts, you can spread them all across the whole north-south US. And the other thing that is important is that the wind and solar could be enhanced by a DC network of this type, because you could trade the availability instead of having to run generation to control it. And I'll get into more of that. The other thing with, it just gives you a breakdown on the $50 billion. Oops. Frequency response is small, but it has quite a big value for the size of it. And the reason is that there's economic multipliers. When you go to multiple interconnections, you multiply the benefits by the number of interconnections. And almost every other transmission line that has ever been built has always had one source of value. And if you go to 3 interconnections, let's say you have 2,700 megawatts between a partial east, WEC, and ERCOT, you'd almost be equal in size. You could cut the reserves on each of those systems from 2,700 megawatts to 900 megawatts and have a backup system to deliver 1,800 megawatts of DC from the other systems. Now, some people say, well, that isn't as reliable as ours, but I beg to differ with them. If you have 900 or have 1,800 megawatts of generation that has an inertia based on 1,800 megawatts versus 1,800 megawatts coming from an inertia of 500,000 megawatts, which do you think would vary least when you had a disturbance? And so basically what happens is the area with the disturbance would see a frequency drop, and almost instantaneously the DC would give you 1,800 megawatts. So it wouldn't have to wait for 3 seconds to hit the governor response and start back up. So you're starting to respond in 3 cycles, and you come in with a constant value instead of a wavering value based on the traveling waves that go across the power system. Load diversity is the big one. When Miso went together, it took 26 balancing areas, put them together, and we cut out 4,000 megawatts out of a 100,000 megawatt load. That's worth about $4 billion. And nothing had to be done except we changed the way we dispatched the system. And then we've improved the system to work better since then. I'll get into more of that later. Wind diversity. Wind has a geographic diversity to it. Miso is large enough to see that. And it's about 600 miles. The correlation coefficient between wind on this side and this side drops to about 1/10. That means this wind doesn't have anything to do with the pattern of this wind. And when you aggregate those wind patterns across the US together, you can raise the capacity credit for wind. Capacity credit is the translate into deferred or displaced generation, which transmits into money. And if you delay a combustion turbine, you're displacing $680,000 worth of investment. And so by aggregating the wind together with transmission, you can raise, at least in the eastern connection, you can get the capacity credit for wind to be about 0.25. And in Miso right now, it's 0.13. So it's 13% capacity credit. But if you go to a small system, like when Miso first started, it may be in a range of 2%. So you're getting value out by aggregating transmission.
Yeah, on that load reduction, 36,000 megawatts of load reduction.
Mm-hmm.
What exactly do you mean? The load
your coincident load goes down. I should have used that word, but I only have so much slide there. So, the other one, solar diversity, we really don't know much about that because we don't have good data yet. And but I think it'll be in that range too. But everybody's grasping their hands and saying, "Oh, you can't take solar here, you can't," because it's so variable. That's the same song and dance we heard about wind. When I started with wind in 2002, WEA told us that the maximum amount of wind that you could put on Miso and SPP together was 10,000 megawatts because we couldn't control the system any more than that. Well, we have 12,600 megawatts in Miso alone, and we're controlling it quite well. And one of the reasons is because of the diversity in the geographic location of those generators. And we found out in the EWIT study, is Eastern Wind Integration Transmission Study, not only do you get up to about 25% capacity credit, but you could reduce the variability of wind by a factor of 3 if you aggregated them with transmission.
I go out on a limb and say how much wind you could put in myself?
There's no limit.
100%.
If you had the right storage, yes.
No storage. Would you go with no storage?
I wouldn't go over about 25% at a maximum. And the reason is because after you reach that, you have to export considerable amounts of wind. That means that your neighbors couldn't go to 25% because they'd have to absorb it. But if one person did it, they could probably go 40. But you need somebody to take the extra energy to keep it economical, and you need a big market to dump it in. In fact, Minnesota's looking at that right now, 40%. Area control area, the U.S., if you look across the U.S. and you averaged all the area control area, it's a very, very small number. And that is the most expensive control on the system. It's regulation. And you could exchange those across with a DC tie. They're fast enough to just pool the area control areas. This is system from the 500 kV Miso over to Houston in 2 different areas. This is a nuclear power plant. For 2 lines, we'd have to separate it so that each line would carry about 1,100 megawatts or be capable of it. But if you lost one, you'd have to still have 1,100. So you'd split the loading on that line to about 550 apiece.
We had some of our grad students spend their summer down in beautiful Beaumont area.
Mm-hmm. And what would happen is that you could get 1,100 from Miso if this plant went out or something else. Problem is Houston doesn't have quite enough to give back to us, so ERCOT has to make either a transmission improvement or we need to take one of these lines up to Dallas. We're working on that system. This is the big system. This would tie everything from Nevada, possibly California, all the way over east. And we cut out a big section called PJM, Ontario, New York, New England, and Hydro-Quebec and the Maritimes. So we don't think we can build an economic system with them. We can build with other people. And the reason is the transmission costs are more reasonable in these areas. And we're more interconnected. We're not very interconnected east and west with PJM. We only have a 4,000 megawatt interface with them. But Hydro-Quebec has 1,700 megawatts of load or frequency obligation, and I think this group could make their own separate system, and we'll have our own separate system. Someday we may tie them together. But until they get their system built, we're not studying it. If we include them, they'd sink the whole system with the economics. So we partialed the system out into pieces that would work and would not work. And what this does is it ties all the major generation and loads together in US. This is your solar load down here, tied to wind up in Wyoming, up into this area. This is an interesting area. The wind up there has got about a 50% capacity factor, and it operates mainly in the daytime. Our wind is about 35 to 45% capacity factor, and it blows mainly at night. So this is a very valuable wind resource up here. And the reason is the Rocky Mountains produce the wind coming down off the mountains in the daytime. And if you put that system together, it's worth about $20 billion, and its benefits are $25 billion. So I think this is feasible. And here's the system I was talking about. Is the partial east is Eastern Interconnection has about 4,500 megawatts of obligation for frequency response. And we can partial that out into two parts. This part, PJM plus all these other people, has about 750 that matches up with Hydro-Quebec that has 1,700. And our partial east is 2,750 that matches with ERCOT and WEC. And when you have a match in the capacities, you get the optimum use of transmission because each person gets an equal benefit. So the economics of exchanges is what would support this fractionalizing the U.S. in design in the Eastern Interconnection, and also it gives you the partners you should work with. Totally, you could take off about 7,000 megawatts of spinning reserve with frequency response. And there's less transmission is estimated to be required for splitting the system than if you combine them. We still have the AC systems that can give the parts that we need to hit the 4,500, but we don't have to ship power out of the other three-quarters of the United States to the Northeast where the transmission costs are so high. So the economics tell you pretty much what you can do and what you can't. And like I said, now, why now and not before? They didn't have voltage source converters that were big enough, and they didn't have DC breakers. Well, you can make a DC network that operates much like an AC network for frequency response and all these other products, and have it contingent. So if you lose one element, it would automatically pick up the schedule of the others. The other one is economics. DC lines are lower in cost over long distances than AC lines. And VSCs are fast enough to be reversed to follow wind and other variations. The present load commutated DC systems, they take anywhere from about 30 seconds to maybe a couple of minutes to reverse. And that's too slow. So the VSC is the technological advance that makes it possible to build these networks. The other one is VSC's supply reactive power. They supply plus 35 to minus 500, or 35% to minus 50% of their rating at full power. And if you put a 50% capacitor on there, you can bring that all up to positive reactive support. And the main thing that happens when you lose a big generator, you not only lose the power, but you lose all the reactive power from it. So you're getting a voltage drop into the area where you lost the generation. The DC can supply the reactive power to give you voltage regulation, which makes the AC system work better, plus the DC power and reactive power. And when it's not running, it can be used for voltage support. And to put 1,000 megavars of voltage support into an area, it's pretty good regulation.
Where do we see applications of these VSCs on a large scale basis? Anywhere?
Not yet. They have small ones in Connecticut to Long Island.
Yeah.
They
I
have.
don't know if they ever use that connection.
Yes, they do. In fact, they used it to reestablish Long Island in the blackout. And they have in Australia, and they have a lot of them being planned for offshore to bring wind into Europe. And Europe's looking at a 500 kV network to integrate Europe. And one of the reasons they're going to 500 kV is they're going to use cable in a lot of areas. VSC can also use cable. It's about 3 times the cost, but you can underground the systems. Right now, they're only at 300 kV and they're testing 400 and 500 kV. It takes them a year to do the tests. And the one thing that's really handy is VSCs can black start an area, which ought to make FERC happy. We could black start New York from California with this system if we had to, but we would probably use the intermediate systems. So you get an area that's impacted and you get the support from the area away from the impact. So a lot of the other generation usually gets impacted at the same time. Well, this would be an independent source. Was there a question? Yes?
Yeah, so our flood machine, I don't know if you by black start or
The DC of VSC looks like a generator with a control on it, except it's faster. And you'd put a ramp on it, let's say of 1 second. You go from 0 to full power in 1 second and maintain the voltage. You could bring up 1,000 megawatts in maybe a second. Well, you could get the power from there. It doesn't matter where it comes from. It could come from South Carolina, but I mean, if we had to, we could go that far on that network.
You know the term black start capability? No, so so black start is what you need when you have an outage. And then you need to have the source of supply so that you can restart all your auxiliary systems, and then you can restart and restore the system. So it doesn't matter where it comes from, but if you've got an HVDC all the way from California to the East Coast, then you can do it.
Mm-hmm. But we'd pull it from where we need it, and we could bring up power. It wouldn't be a big issue for a network. Most of the black start today is done with hydro or combustion turbines that have an offside either diesel generator support or something to get it started. They start them with batteries and then step them up, and it usually takes hours to bring a system up, or days to bring a system up from black to connected, depending on how big it is. This would be much faster.
Well, I think you should also add the complexity. Now that we have so much renewable resources,
right.
We can't rely on them for black start, so we still have to have dedicated resources just to do the black start, because we can't tell the wind to blow.
Well, yeah, but if we had it connected across the entire U.S., we'd probably have some wind. And if they were synchronous machines or 4-quadrant machines, we could start them use them.
Committed
market
Right.
for some other purpose.
Yeah. What is the difference in DC designs? Is we don't have to go through a weak seam area between two large systems to get to the large load areas. We can just skip over them. We can go from large terminal to large terminal to a large terminal in a big load area or a big generation area. And there aren't as many of those in the US as there are AC terminals. In our models, we have 40,000 buses. In the DC model I showed you, there's 20 buses. And anybody can figure it out. It's a lot easier to computate something from 20 buses than 40,000 buses. And especially since the 20 buses just use Ohm's law, and you can use EE 101 to calculate the power flows. You don't need a great big EMS system. And that gets back to fewer elements and simpler. Cost allocation is simple. If you don't participate, you don't get the use of it. It's pretty easy. Right now in AC systems, everybody gets a free ride. When somebody builds something, everybody benefits from it to some degree. Loop flow is minimized. Loop flow is the difference between what you schedule to a place and what actually flows on your lines between them. And we have complicated loop flows out of Miso, which is in the middle of the United States, with TVA, which is in the southeast, and SPP in the southwest. We have a system that goes right down the middle of those two systems. And when you run AC, it just blooms out and comes back. So we impact a very large part of the transmission system with AC. DC, we can go right down the bowling alley and end up at the pins. We don't have to impact the neighbors. And benefit leakage is meant.
Are there any loops actually?
No. There is a little AC counterflow that you'd get from the DC injection, which would usually be in reverse to the way an AC system would load it. So it would probably unload their systems too. But AC systems leak benefits, because I'll show you some slides on that. And other participants get benefit from that. There's research to be done. There's control system interfaces with markets. That's a major one. All the things that I did are assumptions. And when you deal with a stakeholder community, assumptions don't go very far. Nobody agrees with your assumptions. You have to convince them that you're right, or you're going to get another set. Damping controls for oscillations. We have had an AC system that very few people understand. When you get a loss of generation in Georgia, the traveling waves from that disturbance roll all the way across the United States, hit Canada and the western grid, which is an open interface, and it reflects off there and comes roaring back, and it goes back and forth about 10 times before it settles down. The DC system, you could actually see it coming and start taking generation off, so when it got there, it wouldn't make a big impact on you, and when it reflected, it wouldn't reflect back to the same degree. WEC has a 1/10 of a Hertz oscillation. That system I have connects one side of that to the other. We could probably damp out the 1/10 Hertz oscillation. The Eastern connection has 1/4 Hertz oscillation. I don't know about that one because that connects to New England to Miso. And it goes all the way across the United States. It's like taking a big bowl of Jell-O and shaking it. That's what it looks like if you plotted it. All you see in textbooks are these curves that go like this, you know, nice sine waves that damp out. Well, When you get out in our part of the world, you got this nice sine wave that damps out, but also you get this reflection that comes back off of our edge of our system. So you got one going like this and one going like this, opposite, or out of phase with it, and you get a really messy sine wave. And so it is hard to tell what you should be damping, which one is the most critical. And all the reflections don't come back at the same time, because one of them goes clear to Manitoba, the other one goes to western North Dakota, and we got reflections off of Nebraska and down into Texas. So we get different reflection speeds.
We've shown that to them for the WECC.
Mm-hmm.
See that, just visualize it.
And this would give you a means to handling those damp. We have a damping control on a DC in North Dakota, or in Manitoba. It's 2200 megawatts of real power damping, and we can damp the quarter hertz for most of the United States with that system. This is a little more complex. This is probably only for people in Georgia's class. But when you have a power system, it has a price supply curve. The price over here and the supply is, you move up the line, you get a higher price. If you have two systems running together, one may run at a lower price. And when you exchange power between them, you don't divide the cost of the energy or the price of the energy. You divide energy. And this part will come down farther than this part goes up. So you get a new price curve somewhere in the middle. And the power on each side is equal. So when you're programming the analysis for this type of thing, you have to think in these terms, because you got two systems with different characteristics. And when you hit the same price, you've hit the optimum minus losses. But the power flow won't, the power flow will be equal, but the price differences are not equal. This guy will always make more money than this guy. And that causes problems with people. So you got to come up with a solution that shares the benefits on most transactions like this. Okay, the other thing is the price curve used for a multi-region dispatch. If you knew the price curve extended for one person or price curve extended for another person, you could use the last 5 minutes from the other person to optimize your dispatch for the next 5 minutes. And it gives the native area a little more advantage with the revenue. They get a higher revenue than they normally would get, but with a large generation basis and prices, you should get more stability out of it and see less spiking. So even if you're off 5 minutes, you still should get a benefit. Nobody's solved this problem yet. I have ideas, but I haven't got anybody to do it yet. This is a study that we did in 2006. These are all different companies across the United States. This is Ontario Hydro in New York, SUNY, which is in New York, and this is Miso in Nebraska. And the power goes from a high over there in the New York area and distributes itself all the way along the system. The black line is kind of an average, so you can see the trend. But what that says is if this guy sells to that guy, everybody in between gets a little bit of benefit. And they don't pay for it. And this is what I call system leakage. This comes out of a ProMod run, which is a production cost run. And if we build a system, these are the people that would benefit from them. Southwest Power Pool's over here, Circ's over here. Circ gets a big benefit because they're in the middle. Miso's here, PJM's over there, down here. TVA that doesn't want to do anything with us, they benefit over here. So if you build an AC system to transmit a lot of power, this one transmitted 26,000 megawatts of wind across the U.S. with 765 AC. Now, if you do the AC system, this is probably what you get. You get a lesser value here and a greater value here, but you get a distribution of the value across. Where if you go DC, this price comes back to here, and the guy that supplied the energy is much better off than he would be down here. So there's a difference in the financial performance of AC and DC with respect to the markets. And that's why we do the cherry picking with the DC, is because we want to get these benefits to pay for the transmission. We don't want to get these benefits. And that's it. Okay, questions?
How realistic do you think this is of getting built?
I think we'll get the first steps built in my lifetime.
That would be the one down in
That'd be between us and ERCOT and between,
Beaumont area.
yeah, and or Dallas and Houston. And the next one would probably be out of Coal Creek to Coal Strip up in Montana and go down the eastern range of the Rockies.
So what's a ballpark dollar value per mile? How would you price it?
Well, the terminals are about 310 million each, and the lines are about 2.3 million per mile. But that
How many miles?
doesn't matter.
You got to pay that 600 million first.
Yeah.
Well, you only have to pay one of them if you need it for less miles,
Yeah,
because the first one is already built.
yeah. But the nice thing about a voltage source converter too is it could be tapped in the future. Load commutated converters are very expensive and require a lot of detailed planning to make sure they work together in 3-terminal operation. Or a voltage source doesn't have as much problem with that. That's why they're using them to pick up resources from wind plants from multiple areas.
So this voltage source converter would be part of the converter.
That is the converter.
That is a converter?
Mm-hmm. A voltage source converter, if you ever get to San Francisco, there's one that goes right into downtown San Francisco. It's 400 megawatts, and it runs from a cable through the bay from Pittsburgh, which is South Bay, over into San Francisco, East Bay,
Yeah.
over into the old coal generation area of San Francisco. So they already had the transmission there. They just replaced the coal plant with a voltage source converter. And a voltage source converter would be about 6 of these rooms, maybe a little more. And it'll be in an industrial type building. It'll look like a big farm building. And there's a little bit of substation outside, but they could put that inside if they have to too. And so the aesthetic thing of if you've ever seen a DC substation, they're huge, and most people don't think they're very pretty unless you're an engineer. But they're, you know, you're probably talking 20 acres for those things. And the voltage source is much more compact and will fit into an urban area much better. The other thing, the DC lines are not that big. 600 kV DC line will fit on a 345 right away. And if you get 320 DC, you can run it down a 115 right away down a road. So they're not huge compared, they're smaller than AC towers, but you only got 2 conductors and a shield wire, or 2 shield wires.
To build this, you need somebody who's willing to put up the money and get a syndicate going. And are any of the utilities showing interest?
Yeah, but they don't want to talk about it. FERC has made everybody in the transmission area competitive. They won't tell you anything anymore. And the reason is they're going to have them competing on regional transmission. But utilities are interested. We have developers interested. We've broken the project down into sequences. Like that Texas one's about $1 billion, and that's within an individual developer's purview, and the one up in North Dakota and Colstrip's about $1.5 billion. So that's in a developer's purview.
Is it being built?
No, we're just talking to them right now and trying to get them to understand the differences in the constructs. People your age will build this, not me. It'll be 20 years before this is all done.
Don't look at me, okay?
Yes?
So when you're trying to plan something this far out, 20 years out, you just gotta look at what are some alternatives. A lot of research in storage, for instance.
Well, this would make storage work much better because you could use it across the system. The other thing it does is it relieves the need for a lot of storage. So you get storage back into the area where it operates best rather than just in these peaking conditions. Storage, you have a lot of capital costs, and you have to have quite a bit of energy out of those to pay for that capital cost to make them competitive. And if you take away all the fuzz and the spikes off the top, you get a much better product to serve with your storage than this.
I guess my question is, if you would see, solar has seen a crazy decrease in cost, right? If you would see something similar in storage, at that point, that may be more cost effective to distribute storage throughout the system.
Well, the best storage in our system, according to our analysis, is CASE, compressed air energy storage. That is the only storage that competes. And until gas prices get about $5, it does not compete. Present time, the lowest cost system is just build plain old flat gas plants. But we also have Manitoba Hydro sitting north of us with 9 months of storage, not days or hours, months. And they can actually arbitrage wind from spring into the summer or winter into the summer. And we haven't fully used that system yet. So until we get Manitoba maxed out, which requires some more transmission generation, in our area, storage isn't competitive. But in other parts of the country, it may be. Yeah.
As I asked this to the NAP speaker, I'll ask it to you. What do you think the biggest risk Miso faces going forward is?
Internal destruction.
You think that's it?
The stakeholders will start to fight.
Civil war.
If you can't keep the stakeholders reasonably communicating with one another, they'll separate. That's probably the biggest issue, or you'll lose customers due to that type of thing. And I was telling George that we built or approved in 2011 a $5.2 billion transmission project. The Miso system is worth about $15 billion present worth. So we added a third of the present value of the system in transmission that will be built between about 2015 to 2018 or 19, in that range. And that levelizes the prices across Miso. So there's only $2 or $3 difference all the way across Miso. Most of those differences are losses, not congestion. And it delivers 21,000 megawatts of wind that can reach all of Miso. And they call it multi-value. And the benefit cost ratio of that was 1.8 to 1. So it pays for itself. And
our Sydney to Rising line is part of that, isn't it?
could have been. I don't remember.
Yeah, because they're building river to river.
Is that or American?
It's Ameren.
Ameren? Yeah, it is then. There's 17 lines. And the reason for that, it's very similar to this. And that's why this thinking came over to national. We had 26 balancing areas, and they were all designed to be run with my generation in that balancing area to my load. And the transmission between the areas was only for a few reliability operations. They didn't have a vast interconnection for sales and purchases. They had some, but it wasn't very vast. So we had 26 little islands that weren't connected, and we connected them. And that made that system able to operate as one balancing area versus 26. And that cut out 4,000 megawatts of generation and about 2.5 billion in total benefits and per year. And the reason is that all this diversity, because we're over 650 miles wide, we have physical diversity in our system. And people, when you average generation out, the coal plants run better, the nukes run better, everybody runs better because you're not trying to regulate with your generation. You take the aggregate, and a lot of the ups cancel the downs, and you end up with a smoother system. And there's value in that, and that's what this proposal does. It finds that value on a large scale, and it takes it out of it. And technically, it could be done in the future years if these guys design it right, you know?
It's not an issue. The issue is, I was thinking, a state like North Dakota, South Dakota should support the building of one of those converters at their site so that they can sell their power into other states.
Well, that's part of it, but the real justification is the capacity credit. And
For
the
all kinds of reasons, because that would
Yeah.
come back to the producers because they sell that capacity
right.
to them. But I just don't see the industry organized in such way. It's totally dispersed. So there would not be the kind of consortium who would get together to pay that $300 million to build one of the converters, plus maybe the part of the line.
Well, in Texas, if you just did that Houston one, the benefit cost ratio is 2.5 to 1. That's in the no-brainer category.
Yeah, I know, but
That
some
means-
people still walked away from that.
Yeah, some will, but there's also people out there called independent developers who would go out and develop that line, and FERC could be right on their back to make sure it worked. So you got to remember, FERC has got a finger in this too, and they are pushing. We're no longer just able to be independent.
It's not clear that FERC necessarily understands everything, but
No, but they think they do. And they will eventually come to be the people that do, and if we don't educate them, then it's our fault. But it's a lot of opportunity for people to work on too, because $20 billion is probably about 8 to 9 times MISO's usual budget.
Well, we're training out the engineers to do this.
Yeah, well, your power electronics people, your markets people, your power transmission people. Somebody's going to run a lot of AC too to figure these out. It'll be an interesting situation, I'm sure. Okay. Any other questions? Okay. So I got to.
I call just-in-time manufacturing.
Yeah, I got to run.
Thank you.
I got an airport. I've got to get,
Fly up to Minneapolis?
yeah, we got a 40% wind meeting in the morning. I have to be at
6 o'clock?
8:40 out of Indy.
Oh, you're going out of Indy. Okay. You got the time zone down, right?
idea how to get the IP address for these things. This is what my lab partner was saying.
You're on a different time zone, so you gotta
I figured that out. I have the time,
silent.
but it's going to be very.
Thanks for visiting.
That was good. Is anything on this written up?
Yeah.
Are you letting me get that?
Going through the theory, but we've learned more since we found it. So it'll probably be, I think I'll put it
Really, hidden machine.
like in.
Yeah, I mean, it's good for students to 10,000, something real. Oh, yeah, like for a computer, that makes computer science.
It's a very non-technical group, that's the problem.